Right, well, this is the second half of this morning's session. Professor Tim Palmer will be speaking to us. Title's right here. Professor Palmer is the Royal Society Research Professor at Oxford. That's a great job to have. I wish I had it myself once. He can just go anywhere he likes, and he's at Oxford, and that's his bad taste, but that's... he's been a member of the IPCC for, I can't believe, from its inception. It was that, okay. So he's seen through the various rounds, and that's what he'll be speaking to us about. He's a fellow of the Royal Society, and in addition to getting money out of them, he started his life in fundamental physics and continues to do that. He was telling me that he works on gravitation about 20% of his time, and he explained to me why and how he's able to do that. Tim.
Yeah, so my background actually is in physics, mathematical physics. I'm not going to use much mathematics, and the ones that I do use will be more for decoration than for any sort of important purpose. So climate change clearly is a very polarized subject, as the title suggests. You know, people have taken various positions on climate change. I just want to briefly review those. So I guess that's the thing. So we can easily think of catastrophes that will or may happen as a result of climate change. Things like the disintegration of large parts of the Greenland or Antarctic ice sheets, leading to major sea level rise, rapid sea level rise. The idea that drought, so we've seen droughts in Europe in 2003, which devastated the crops in that summer, droughts in 2010, which devastated the Russian harvest, continuing drought in California. One of the catastrophic implications of climate change is when these start to happen contemporaneously, then really the world's food supply will be under threat. One topic which I don't think receives actually as much attention as it should do is this notion of what in meteorology is called a wet bulb temperature. So when you measure temperature with a little piece of cloth which has been soaked in water, measure the temperature, that tells you, in a sense, how the ability of the body to lose heat by perspiration. And when the wet bulb temperature reaches essentially body temperature or close to body temperature, then that's telling you you're now in an environment where you cannot lose heat. And that's an existential problem. And last summer, large parts of the Middle East rose very, very close to this limit. And many of the projections of climate change suggest that will become increasingly commonplace. So that is clearly a kind of an existential problem for many parts of the world. Super hurricanes, we had Haiyan, which hit Philippines a couple of years ago, record-breaking wind speeds. I mean, these kind of very intense cyclones are projected to become more commonplace. So there's lots of scenarios where one can point to catastrophic types of events, and there are many books which sort of emphasize that side of the spectrum. A very famous one is James Lovelock's Revenge of Gaia. It paints a very, I would say, apocalyptic vision of the world. Then, on the other side of the coin, we have our president-elect, who claims it's a hoax created by the Chinese. It seemed from the media that he was softening on that position a week or so ago, but then picked this guy, I don't know, but apparently a strong climate change denialist to lead EPA. So perhaps the evidence is not that great that he's changed his views that much. But as the title suggests, there is a third way, and sort of superficially it seems, kind of reasonable sort of middle ground, if you like. And I think the most articulate proponent of this philosophy so-called lukewarm philosophy of climate change is science journalist Matt Ridley, who actually gave a lecture at the Royal Society in the Global Warming Policy Foundation's annual lecture, this being an organisation whose principal aim is to repeal the Climate Change Act here in the UK. So the lukewarm philosophy goes that they accept the basic science that carbon dioxide is a greenhouse gas, that the temperatures of the atmosphere are warming, and that indeed the two are causally related. So that's a good thing, because then one doesn't have to go over old ground about, basic radiative forcing and all that sort of stuff, which is now, I think, pretty much textbook. So that's all very good, but the stings in the tail is that they don't accept, he doesn't accept, and his colleagues don't accept that the changes in the coming century or so, I don't know what timescale, will be damaging. So the word lukewarmer is really to say that climate change, yes, it's happening, but compared to all the other myriad problems facing society, many of which we've discussed, is kind of low down in the pecking order. So that's clearly an important position, I think, to try to assess whether it's scientifically robust or not. I think if there's one take-home message from this talk, is that none of those three positions, the catastrophe, the hoax, or the lukewarm, none of them is a scientifically rigorous approach. None of them is consistent with the scientific evidence and also the scientific methodology that we apply to climate change. I want to describe that. To do this, I'm going to use one of my favourite toys, the executive decision maker. This is a magnetic pendulum, and it illustrates the chaotic nature of weather. So what we'll do, in fact, if I can get it to work, let's see. Oops, I got it to work earlier. Didn't seem to want to. Oh, yes, here we go. So it oscillates irregularly and aperiodically between these four magnets. The executive decision maker is to guess which one it'll stop at. The sequence of the magnets is very, very sensitive to the starting condition. So if I'd started the pendulum even minutely differently from where it actually started, the sequence of magnets that the pendulum would have visited would have been completely different, completely uncorrelated. So one can think of these, if you like, magnets as states of weather. This could be a kind of warm weather state. This is a cold weather state. This could be kind of wet weather. This could be dry weather. I don't know, different kind of regimes of weather. And in a sense, this illustrates the difficulty of trying to forecast the weather any period of time. And indeed, one of the common criticisms or queries people make about climate change is to say, well, if you guys can't forecast, more than 5 days or 10 days or something ahead, what chance is there to say anything about a century ahead? And we can use the executive decision maker to sort of clarify at a conceptual level the difference between weather forecasting and climate forecasting. So what I'm going to do now is rerun the pendulum, but now sliding a little wedge underneath like this, and off it goes again. And again, the pendulum is following a very erratic and irregular and indeed chaotic, as before, chaotic trajectory. But if you look, you'll see it's kind of biased towards the yellow magnet, which in my parlance was the warm weather. So, but occasionally, perhaps as you just saw there, it makes an excursion to what would have been the cold spell, but in this case, it eventually settles down on the yellow magnet. So what we're doing is sliding the wedge is biasing the statistics of weather. We're making the warm weather states a bit more likely. We're making the other ones, in some sense, less likely. And that's the essence of, that's the main difference between climate prediction and weather prediction. Weather prediction, we're actually trying as best we can to predict the actual trajectory of the pendulum bob over some finite horizon into the future, which may be a few weeks or even maybe a few seasons now, as I'll talk about. But with climate change, it's a completely different type of problem. We're saying we know or we believe that our emissions of CO2 are changing the atmospheric composition of the atmosphere in a certain way, how are the statistics of weather going to respond to that change? And an important point to make is that the response is not a kind of a simple linear one. It's not, it's the change. If I were to slide that wedge in very, very slowly and look at how the statistics were changing, it wouldn't be a simple kind of monotonic function. It would be quite irregular. So the wedge, in some sense, is our is what we're doing to the atmosphere by emissions of CO2. This is the famous Mauna Loa CO2 record showing we've now topped 400 parts per million. You see the nice annual cycle as the biosphere brings in carbon, lets it out again. This is the much more irregular surface temperature record, showing these periods where, in fact, global temperatures, global surface temperature was, if anything, decreasing. And this famous period up in the late 1990s, early 2000s, where the surface temperature, at least, seemed to be somewhat stagnating. These things are quite subtle, by the way. This depends crucially on how well you think you've measured the Arctic temperatures, where historically there haven't been many observations. But you'll see we've leapt up again to quite large levels, so we're now well above this 1 degree increase over the late 19th century. But the point I want to make is that you would expect in a nonlinear chaotic system like the climate that you wouldn't expect to see a kind of monotonic increase in temperature along with the steady increase in CO2. It's not very dissimilar to thinking about the annual cycle. As we go from winter to summer, every day in Cambridge, the sun, in theory, gets a little bit higher above the sky, if it's not too cloudy, from the winter solstice through to the summer solstice. But, the temperature certainly doesn't rise monotonically with that. We can get a cold spell in February where we seem to regress back to darkest winter. So that's just chaotic variability. And that cold snap, by the way, in February is unpredictable from if you're in December. And similarly, this slowdown, which was believed to be mainly due to ocean dynamics in the Pacific, is not something that is predictable. Just as those magnets, the transition between the magnets is not itself predictable. Okay, so what's the problem? The problem really is that we don't know actually how thick that wedge is. It's not a simple matter of just saying it's carbon dioxide. And the reason is there's lots of stuff that happens which potentially amplifies anyway, the effect of carbon dioxide. So even in the 19th century, the famous Irish physicist John Tyndall realized that water vapor, gaseous form of water, which is transparent to visible light but opaque to infrared light, was, if anything, the dominant greenhouse gas in the atmosphere. And this is another sort of reason why water is so essential to life. It forms a blanket which keeps the Earth's temperature at a habitable zone. And then Svante Arrhenius, the famous Swiss chemist, realized that with increasing levels of carbon dioxide warming the atmosphere, that was likely to have a positive feedback effect in increasing water vapor in the atmosphere. The warmer the atmosphere, the more water it can hold. And that then amplifies the direct effect, the direct radiative effect of CO2. But there are lots of other things. Ice albedo is famously accelerating the warming in the Arctic Ocean, that as the ice melts, less sunlight is reflected back to space and more is absorbed by the darker water. And just as in parenthesis, some of the first papers on modeling climate change in a full sort of three-dimensional climate model were done at GFDL by Suki Manabe. And two of the predictions made, this is in the 60s, about future climate change were, one, an accelerated warming in the Arctic, which has happened, and secondly, a cooling in the stratosphere. So once you're above the essential kind of height where the Earth is radiating to space, the level at which CO2 is mainly radiating space, the atmosphere will cool. So both of those things have been observed. So those are actually predictions. People often say, oh, what have these models ever predicted? Well, those are two predictions. And then there are other things, methane, the release of methane from permafrost as the permafrost melts, and then the potential for the carbon cycle, if there's significant dieback, for example, due to temperature or water stress, that reduces the ability of the biosphere to take in carbon, increases carbon concentrations in the atmosphere, and similarly the oceans, the less the carbon is available to dissolve in the ocean, the more it will remain in the atmosphere. So these are all sort of amplifiers. The one, though, that is really uncertain and probably is the single most important of these feedbacks, well, I would say full stop, actually, because in a sense how important these are depends on this, are the role of clouds, the liquid and ice form of water. And clouds actually play two roles. So very high level cirrus ice clouds up in the sort of high atmosphere tend to trap heat, so they act as a blanket, but low level thick sort of stratus clouds in the boundary layer, lowest kilometre or so of the atmosphere, tend to reflect clouds. So the extent to which clouds will amplify or damp with climate change depends on how much low level, so they amplify if low level clouds decrease and high level clouds increase. This is actually the direction most models suggest is happening, but I would say that our physical understanding of that is poor, and so confidence in that is poor. So to try to understand these things, as I say, we have these models. They're based on ab initio laws of physics, so Isaac Newton, Max Planck, quantum mechanics, and this people probably don't know is Rudolf Clausius, who was one of the founding fathers of the laws of thermodynamics, this being the second law of thermodynamics, the entropy he derived, or he invented the concept of entropy. All these three sort of basic laws of physics, mechanics, quantum mechanics for how photons are absorbed and re-emitted back to space, and the thermodynamics, thinking of the climate system as a thermodynamic engine, these are all encoded into trying to represent climate variability and climate change using laws of physics. This is my equation, which is therefore more artwork than anything profound. But this is Newton's laws of motion. So I showed force equals mass times acceleration, which you're probably familiar with. This is an expression of force equals mass times acceleration for a fluid like the atmosphere and the oceans. It's what mathematicians will call a partial differential equation, and indeed a nonlinear partial differential equation. This velocity term sort of multiplies here twice, so that makes it nonlinear, and that nonlinearity makes it very complicated to solve, as I'll say. Just to say, it always strikes me as a remarkable feat of mathematics that with some 20-odd symbols one can basically represent a system which extends, from the 10 scale, motions on scales of tens of thousands of kilometers up in the jet stream or the big ocean gyres, right down to, the turbulence of me talking and the air coming out of my mouth. This is all together described by these 23 symbols. So I often think of it as a work of art, but not actually a Renoir, more like a Russian doll. And the reason for a Russian doll, this is a very special Russian doll, because this Russian doll unpacks into very, 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 very many Russian dolls. And in fact, billions of Russian dolls, because if you really want to represent all these scales from the largest scale on Earth, so the jet stream scales, meanders of jet streams, which are very large and large scale, right down to me talking in this room, then you'll need, so the idea is each of these Russian dolls represents actually an equation which you have to solve on a computer. So if you want to solve this on a computer, you've got to unpack this very beautiful piece of mathematics into billions of individual equations, which which then the computer tackles one by one, so to speak, or in parallel on a massively parallel computer. The problem, of course, is that even with the largest computers in the world, we can't do this. We can't go right down to these sort of almost down to molecular scales, so we actually end up having to chop Russian dolls. And a typical climate model of today, the one, say, that would fed into the last IPCC report, would be able to represent scales in the atmosphere and ocean, so from this larger scale, maybe down to around 100 kilometers. So weather systems, this being low pressure system tracking across mid-latitude somewhere, is pretty well, broadly speaking anyway, resolved. But say an individual thunderstorm, which might have only a scale of, say, 50 kilometers or less, and these are crucially important for determining the thermal and momentum and moist structure, particularly in the tropics. These are typically unresolved in these global climate models. And that's really the key problem when we try to predict climate change, predict how the statistics of the magnet will change with this wedge being pushed underneath, that we can't resolve some of these key climatic features. So what we have to do is represent clouds and sort of turbulence and small-scale topographic features and various other things which can't be resolved by much simpler formulae. So I've got this rather sort of ugly block of wood to represent a rather crude formula, if you like, crude by comparison with the so-called Navier-Stokes equations, which are beautiful pieces of mathematics. These are much cruder, but they have the advantage of being very, very computationally fast and represent in an approximate way things like clouds that the simulator can't resolve. And that's, at a sense, at the heart of the problem and why there are so many uncertainties about climate change prediction, which I'll talk about in a minute. I just thought, however, it's worth stressing that these models are playing an increasingly important role across a range of environmental inputs. They're basically the same models, actually, as is used for weather prediction, and increasingly now things like El Nino prediction and the effects of El Nino. Rowan Douglas actually very briefly mentioned weather prediction. One of the remarkable things about the last few decades is that the number of deaths from things like severe tropical cyclones has really plummeted. And certainly one of the reasons for that are much, much more reliable forecasts of tropical cyclones and hurricanes on sort of a 5-day timescale. So people can evacuate or go to shelter or whatever, providing the warnings are disseminated to people. So that's been a real, I think, sort of measurable impact of our ability to solve the Navier-Stokes equations accurately. And this sort of slightly longer-term prediction is becoming increasingly important, particularly in the tropics, in trying to predict the effects, as I say, of things like El Nino on droughts or floods in the tropics. I myself, for example, have done some work on how El Nino affects rainfall in southern Africa, which then affects the probability of epidemic malaria. So the ability to give aid agencies advance warning means they can go out and give extra bed nets or spray stagnant areas ahead of the rainy seasons and therefore sort of mitigate some of these disease epidemics. I should say, by the way, in the case of weather forecasting, I think we've reached the stage where the aid agencies really need to be going out and sending to communities, like Haiti and like the Philippines under Haiyan, actually sending out aid ahead of these cyclones striking, because the forecasts are now sufficiently good that they can do that. There is some politics apparently in this, because once you do it ahead of the event, then it comes under development aid or something as opposed to emergency aid. But from a purely scientific point of view, I think this is an area where science can actually help improve our preparedness and resilience. Just moving on then, so obviously these are also, as this is the main theme of the talk, important for decisions on climate mitigation. Increasingly about investment in regional climate adaptation. I've been on a government committee just this year on flooding resilience, what new flooding infrastructure do we need to be planning. So that's going to become central around the world to make society more resilient to climate change. These models are essential in order to be able to have some feeling, not just for, because global mean temperature is an irrelevance when one's talking about regional weather. It's about extremes of drought, flood, temperature, humidity, and obviously wind speed and things like that. There's quite a lot of interest these days in what's called climate attribution. So when we have a severe event, can we say whether or not the probability of it occurring has increased as a result of climate change? And to be able to do that, and the media are certainly very interested, and there's potentially also interest in Rowan Douglas's area of insurance, because potentially then companies might be held liable, perhaps if a weather event was deemed to be caused in part by burning of fossil fuels. I don't know. And then finally, another area where, again, these models will be increasingly crucial if we ever go down this route of geoengineering. So is there a plan B, for example, spraying sulfuric acid into the stratosphere to create sulfate aerosols to reflect sunlight? Okay, well, that's really problematic, because you're correcting a problem, if you like, in the infrared part of the spectrum with a fix in the visible part of the spectrum. So it's not quite clear what the regional consequences of that will be. Will you end up disrupting the monsoons? Will you end up cutting off moisture supply into rainforests? So we need, if we're ever going to take these geoengineering ideas seriously, we've got to be very confident we understand the regional consequences of doing that, and these models are the only way to do that. So because of essentially it's because of these closure formulae, we have to express predictions and projections in a probabilistic way. This is from the 2013 IPCC report, the sort of showing a range of projections from a range of these climate models around the world. These are arguably not really probabilistic predictions, because it's based on a set of models. Each model individually has been, the scientists developing the model have tried to make it the best solution that they see of the equations of motion, but because there's uncertainty in how to close the equations, there's a range of solutions. So I don't view these as very reliable probabilistic estimates, to be honest, but they give some indication of spread. So this is with the so-called RCP 8.5 increasing emissions scenario. This is the highly mitigated scenario, and this is at 2100. So you see anything from almost 5 and a bit degrees down to 2 and a bit degrees. A better, in a sense, a more sort of theoretical way of expressing this uncertainty, although it's less practically important perhaps, but I think it's an important concept, is this notion of equilibrium climate sensitivity. How much will the atmosphere warm, if you like, going from one equilibrium to another where the CO2 has been doubled? Famously, back in 1979, there was a report by a very famous atmospheric scientist, Jules Charny, and colleagues, so the Charny report, which estimated that climate sensitivity, basically based on back-of-the-envelope type calculations, was going to be around 1.5 to 4.5 degrees. A modern-day estimate would have it as a very skewed distribution. So this is trying to kind of vary parameters and see how climate sensitivity varies according to the uncertain parameters in that wooden building block that I showed. And indeed, about 90% of that PDF is sort of roughly between that range that Charny et al. Estimates, so it's quite reasonably accurate. You see there's this long tail out at high values. There's a very short tail down to about 1 degree, which is the sort of the direct CO2 effect. And of course, it's this long tail that is problematic, as we'll come to. So I want to just show one of the arguments that Matt Ridley used to argue for this lukewarming. And this is, seemingly a reasonable thing to do. One could say, well, can we take the observational record that we have? So we've got these global temperatures going back to the beginning of the 20th century. We've got CO2. Can we estimate from that what the climate sensitivity is? So we just fit empirically, if you like, try and find this estimate of how much, because we know how much CO2 has increased over this period of time. We know how much the atmosphere has increased. So can we find CO2? And what Ridley says is the attempts to measure the sensitivity of the climate system using real data is that it's actually much lower than the models assume. So he's claiming the models are sort of biased somehow too warm. There was a paper, there have been a couple of papers actually on this. One by Otto et al., I think, had about 1.9 using observational data, and then this more, there's another paper actually had an even lower estimate. So I think his based on lukewarming was using this. Now, I want to just respond to that because there's a couple of important points to make, and I think a lot of people who are not, if you like, expert in the field actually misunderstand. So, and it's kind of slightly contained in this the last few words, that the climate sensitivity is lower than the models assume. Now, this climate sensitivity is not it's not a parameter or something. It's not a knob on a dial that you turn up or you turn down. So here, you have a climate model, and indeed there are numbers of parameters to do with cloud physics, cloud microphysics, turbulence in the boundary layer, where you don't actually know. You have to go to observations and set those parameters as best you can from the observations. But climate sensitivity is not one of those parameters. It's not something that's set a priori. It's an emergent property of the model. And indeed, when climate modelers do integrations for the first time, they have no idea what the climate sensitivity of the model will end up being. Just a few weeks ago, I won't mention the name, but a very well-known climate institute, I don't want to mention the name because the paper hasn't been even submitted yet, but they ran their model, one of the leading climate models, in preparation for the next IPCC report. And to their astonishment, their model was producing a climate sensitivity of 5.5 degrees. Now, this has been, the parameters they can tune fit to observations they've done as best as possible. So, they were, I have to say, quite flabbergasted, I think, that this is quite outside the pack, and it's very much on the warm end. So what's going on here? Why is there a discrepancy then? The reason is that not only is climate sensitivity not a parameter, it's actually, i.e. a fixed quantity, it's actually a variable. It depends on the temperature. The extent to which cloud feedbacks amplify is itself temperature dependent. And the climate sensitivity that these models produce is actually partly the fact that as the climate warms, the climate sensitivity starts to increase. If you think of climate sensitivity as a kind of local gradient, it starts to increase. So the value actually can't be obtained by just looking at the last, say, 100 years. So how are we going to, if we don't want to estimate it purely theoretically from the models, is there any observational way we can estimate it? Well, some people have tried to do that using paleo data. And there was recently a paper, and in fact there's long been, actually, there's been a long literature showing that estimates of climate sensitivity during interglacial periods are actually where the CO2 is increasing and playing an important role in the warming and cooling and so on, but it's natural CO2. It's not obviously anthropogenically forced. But the result is that the warming, how the warming depends on CO2 is larger during interglacials than glacials. And this recent paper has tried to kind of synthesize the evidence from the paleo data over the last 750,000 years and try to ingest that into this into these IPCC type projections to say, well, if we actually made use directly of estimates of climate sensitivity from paleo data, then actually with this RPC 8.5, it would push the warming at 2100 actually into yet warmer estimates. Now, you know, paleo data is definitely uncertain, and I'm not going to make a strong case that this is, if you like, something we must definitely do. But the point I want to make is that if one does make use of observational data in its full extent, there is really no evidence at all that one would want to discount the type of Charney et al. Or CMIP or the IPCC based estimates on the models. So I just want to, do I have 5 minutes to say? Yeah, I just want to take the last 5 minutes in giving what is my very simple-minded view about how we go from inherently uncertain estimates of future climate to decision-making. Because you know, one of the dangers of just saying everything's very uncertain is that people say, oh, well, that's fine, so we'll just, you can carry on with your research for another 10 years and we'll hold off making any decisions. The problem, of course, is carbon isn't like a regular pollutant. It stays in the atmosphere, or a large fraction of it stays in the atmosphere for centuries, if not millennia. So delaying 10 years is adding to the long-term carbon budget. One key point I do want to make is, therefore, that the scientific, I mean, this is part of the conference, the scientific approach to climate change is about risk. It's not about saying it will be X, Y, or Z, where X is catastrophe, Y is hoax, and Z is lukewarm. The question is, based on these estimates of risk, can we make decisions? So I want to introduce you to Fred, the ice cream seller, Fred has a utility function which tells him how many ice creams he will sell, depending on what the temperature is, he sells many more ice creams. For example, when it's 5 degrees warmer than, say, 25 degrees, then he sells fewer ice creams when it's 5 degrees cooler. So he has a very nonlinear utility function. Let's assume that you are employed as Fred's weather forecaster. So he will ask you what the weather forecast is going to be, and then based on that, he will read off from his utility function how many ice creams he can expect to sell, and he'll stock up accordingly. So if the weather forecast is reasonably predictable, so a weather forecast these days is actually an ensemble of individual integrations, maybe 50 or 100 integrations, with varying very slightly the initial conditions. This is perhaps a situation where the PDF is reasonably sharp, so the temperature is within a degree or so of 25, and this utility function is reasonably linear within the range of the PDF. And so the expected number of ice creams is actually not much different to what the expected number of ice creams at the mode of the distribution 25 is. So that's easy. You tell Fred, you don't bother Fred with uncertainty, actually you just tell him it's 25 degrees, he reads off and he knows 70 ice creams he can expect to sell. That's good. However, suppose on the next week the forecast is much more uncertain. You're in a much more unpredictable, unstable part of the climate attractor, and the individual members of the ensemble have spread out in state space, and now your PDF of temperature, although the mode is still 25 degrees, now there's a big standard deviation. So the question is, how do you advise Fred? You could advise him to, again, so the most likely temperature is 25, and that will give you 70 ice creams. But on the other hand, if you do the calculation, you integrate the utility function over the PDF, you'll get about 120 ice creams because of this nonlinearity. So how are you going to advise him? Remember, your advice is in terms of meteorology, not in terms of ice creams. You could tell him that this is a PDF with a certain standard deviation, but the chances are his eyes will glaze over and not be at all interested. So what you could do is say, what temperature would it have to be, would it have to get to, in order that the expected number of ice creams sold was this, this proper integral of 120. And in this case, it turns out that a temperature of about 28 degrees would give you, a deterministic temperature of 28 degrees would give you about the same number of expected ice creams. So what you could do to keep it simple to Fred is say, plan as if it was going to be 28 degrees, because that will give you the right expectation value. Well, we can do the same trick for global warming. This is some work with Chris Hope here from Cambridge at the Business School, based on one of his impact models. The point being that these impact functions are kind of also quite nonlinear, like the ice creams. So if we took the mode of this, so the most likely warming of 2.5 degree climate sensitivity, sort of plug that into the model, you get about $120 trillion of damage. But if you do the full integral, and it's a kind of combination now of this nonlinear function and this skewness, actually, the two things give you about 400 trillion. So there's over the factor of 3 difference between getting the damage at the mode and the full expectation. So how do we simplify that? Well, we could do the same trick. We could ask what would be the effective temperature that would give you that 400 trillion. It turns out it's about 3.6. So one way of actually communicating, it seems to me, in a way which sort of takes account of the uncertainty, but nevertheless gives you a very sort of definite figure, is to say, even though the most likely maybe 2.5, you should plan as if it was 3.6. So I just want to finish 1 minute, if I could, because today's an auspicious day for me, which I will explain why in a second. Although, you know, I think we can deal with uncertainty and we can certainly make decisions under uncertainty, I certainly feel uncomfortable that our projections do depend sensitively on these closure formulae. And in a sense, it's a problem where we know the laws of physics, we just can't solve them sufficiently accurately. And the computer, so we're basically constrained by supercomputing. Supercomputing is moving on rapidly, and most commentators believe that by the early part of the next decade, maybe 2022, 23, the first so-called exascale supercomputers, this is 10 to the power 18 floating point operations per second, will start to get on the market, start to become available. The problem now, believe it or not, although it may seem odd to say this, in climate research, the climate scientists don't typically have access to the top range supercomputers, or if they do, it's only in a shared access, so we may have a 10% or something. I believe this is wholly unsatisfactory given the important nature of the problem, as I say, across a range of applications. So I've been lobbying for a long time that we should treat this problem with the same kind of ambition that we've treated finding the Higgs boson and you know, looking for supersymmetry. It seems to me that if you're in a part of the world where you can't lose body heat, the existence of supersymmetric particles is probably an irrelevance. So let's find out a bit more clearly what sort of world we're heading for. And I think with a dedicated exascale machine, we actually then can start getting down to these cloud-resolved resolutions. So I put in with 21 colleagues, myself and 20 colleagues, put into the EU what's called flagship project on extreme computing and climate. This is sort of this is a bit like the graphene project or the human brain project. It's kind of €1 billion over 10 years. The committee that will decide on shortlisting, there's been a relatively large number of proposals, so we're not the only one. And the committee that's deciding which ones to shortlist are meeting tomorrow morning. So if any of you know anyone on this committee, for God's sake, phone them up this afternoon. It's your last chance. We will see what's happening. So I don't know whether that will happen, but I feel, you know, I think we know enough about the problems to the argument that we just do more research and do nothing is clearly ridiculous. But on the other hand, simulating climate is an incredibly complex problem. It's not a simple one, and we do, as I say, have to recognize that it's up with all the most complex problems: cosmology, particle physics, nanotechnology, everything which needs major resources. And we have, in the past, done most of this work at the institutional level, and it's a bit like CERN, a bit like in the 50s when individual universities did high-energy physics and they came together and did what no country or institute could do. It's time now to move in that direction for climate simulation. So I'm hoping for a positive, Brexit notwithstanding, I'm hoping for a positive outcome from the EU, but we'll see. Thank you.
Thank you very much. That was terrific. We will take some questions before we go to the general discussion. But may I kick off with a question, which is,
it was very nicely demonstrated through your ice cream thing, the power of thick tails on the right-hand side.
That's right.
Would I be right in thinking that it also makes the expected value, with the spread out distribution, sensitive to the distribution itself? As to say, if you pushed it a little bit further, slightly, would it?
Yes, that's right. I mean, you can. Unfortunately, that's right. You're multiplying a sort of big number by a small number. So I think one has to probably recognise. Personally, my view on this would be to put a kind of, which I think we more or less did here, put a cut-off and say beyond a certain point, multiplying a big number by a small number is not meaningful. Yeah. So let's not do that.
Right. So it's sort of compounding problems in your subject. Thank you very much. Questions? Martin? Are you making the phone call or not? Sorry? Are you making the phone call on his behalf this afternoon? Please do.
Two things. First, I certainly hope you get this project, because clearly it's very important for the world to develop these more elaborate models. But I wanted to ask, since you started off talking about the Matt Ridley tendency, as it were, and I wonder if you would agree that in the political debate about climate change, the issue of the sensitivity factor is one, but surely far more important is disagreement about the long-term discount rate and issues like that. Because if we take not Matt Ridley, but the Copenhagen Consensus, Lomborg, etc., where they consider ways of helping the world's poor, etc., they put climate change low on the list compared to other ways. That's essentially because they take a standard discount rate, whereas many people, Weizmann and Harvard and others, would say that we should take a low discount rate. And that makes a big difference, because Lomborg takes no account whatever of what happens after about 2050, which is the time when these effects become really serious. Whereas if you take the view that we should not discriminate according to date of birth, as it were, then we feel we should pay an insurance premium now for the benefit of those people who'll be alive at the end of a century. So it's really ethics and economics which I think causes a divergence of views as much as differences in the sensitivity factor and the climate change.
Well,
I wonder if you'd agree with that assessment.
I partially agree with it, but I did actually go. I made a point of going to Ridley's lecture, and in fact that wasn't a point he made, and most of it was. I mean, he started off with a little bit about this point that, which I haven't really discussed, that that CO2 has led to a greening of the planet, and he says, "Oh, that's great. That's a good thing." I mean, that's a bit like talking to, it seems to me, talking to a drug addict when they've taken heroin for the first time. And they say, "Oh, what's the problem? It's great." Of course, as climate changes, then there'll be it'll bite back, and the long term is. So most of Ridley's lecture was actually about physics. I mean, he talked a bit about cloud feedbacks. He didn't quite get some of the detail there. But Martin, the point I want to make is that if I could persuade the let's say, these people at least to accept the estimates of risk which the IPCC provide as robust. At least that topples that one, that takes one of the factors out. Now, I agree, discount rates and all the sort of more thorny issues in politics, they're still there. But at least if we, my sort of small contribution maybe could just be to say, let's agree on this, that at least let's agree on the basic physics, because if we can do that, then we can perhaps move on to some of these other things.
Well, since you did this is an academic occasion, can I sort of try to mediate between the two of you? Which is that the discount rate that you would be using for these climate models will be discounting the trade-off between marginal consumption today or output today with output. It's not so much time. And that discount depends on not only on the time, which is the point you're making, but also on the forecast, the sample mean, if you like. I mean, it doesn't have to be, you can integrate it, of course, of the trajectory of consumption. Now, the whole point about, as I see it, I'm not a climate scientist, is that there is a reasonable risk that there will be a downward trend in the output side. That's a reasonable. Now, if that happens, then it will give you a negative discount rate. So even if you were to discount purely because of time, which most parents don't do, by the way, the amount of investment we put in our children basically negates the thought that we discount time. But assuming you do, 1% or even 2%, if there's a reasonable sized risk that there will be a downward declining output, which is after all what that model was designed to do, then you will, if you add that to the corresponding to the Navier-Stokes, the Ramsey equation, you will get a negative discount rate. And if that happens, then of course you're amplifying the damage of the future into the present. Okay, and does that seem reasonable to you two scientists?
Sure. Because the people who are of his convictions,
Yeah.
they tend to be those who believe in technologies
Yes.
solve problems and economic growth continuing.
Well, if that happens, then we shouldn't be worried anyway. I thought the whole point is that there is a danger that we're going to get unstuck. Any questions? Oh, sorry, yes. Yes, sir.
So with $500 million, I hope you get your money, but with half of that, could we restore the water cycle, water vegetation in semi-arid regions where it's been denuded, and restore some low altitude cloud cover, and get a slightly slower warming of the planet? So I'm thinking of the NASA GLACE study and land-atmosphere interactions, the Peter Cox.
I mean, my $1 billion is not to improve the planet, it's to understand better.
What worries me, because by the time we've actually understood how the climate system works, the coal industry, with their communication strategies, will have been so successful that it may be too late to prevent the runaway effects. Or are there things we could start doing now with similar investments?
Well, I mean, this is, this kind of goes probably beyond my expertise, because that's where the so-called geoengineering ideas kind of kick in, which...
it's hard to get agreement on that, but could we do less radical things like having paler roads and things that would be viable sooner?
Would that make an impact? I'm dubious whether that would make a global impact, in my honest opinion.
Yes.
The ocean, to be honest, I mean, the first order effect on the weather systems is the ocean. We've got to start changing ocean temperatures and currents down.
Just a naive question about the...
So I just want to finish that, because some years ago I did a study, when the famous drought in the Sahel, this is back in the 70s and 80s, the common perception that it was due to overgrazing of land. And we showed unambiguously it's due to fluctuations mainly in Atlantic sea temperatures. It's sort of natural, it could be well exacerbated, but fundamentally. So if you had made some radical effects to the local terrain somehow, it wouldn't have removed that basic cause of the long-term drought.
Unless it was in line with the Alpha Guinea winds, and they were picking up moisture as they came towards.
It would have had a small effect.
Yes,
It's basically dry.
All right. A naive question about the mathematics.
Yeah.
The computational task
Yes.
in climate modeling, is it of the sort that can be farmed out to millions of home computers, like search for extraterrestrial intelligence?
Unfortunately not, no, because you're basically, as I say, the crucial part of the calculation is discretizing, you have a grid, let's say, or sort of models I use, actually you have waves. You represent the atmosphere by what are called spherical harmonics, but it's the same thing. Now, these different parts of the model have got to communicate with each other pretty much instantaneously. The speed of the efficiency of the calculation is really determined by the speed of communication. So if one computer's in one part of the world and another somewhere else, the latency is just kills you dead. So unfortunately, cloud computing. There have been projects. So a colleague of mine, Miles Allen in Oxford, has developed a very nice kind of outreach exercise where people can download a kind of simplified version of the Met Office's climate model onto their PCs and then run these very large ensembles of integrations, varying parameters and things. So that's where a kind of parallel system works, but then your model is constrained to be a very simple version of the model. So if you really want to cutting edge resolution and things, you've got to have localized supercomputing.
Yes, sir. Oh, sorry. Well, you start, then you can.
Yeah. To follow up the question on how this sound for climate change would work, how confident are you that if it works on a smaller resolution, you can have a smaller grid, that you will converge to an answer and then it won't adjust? There's still lots of uncertainty there.
Yeah, it's a good question because unfortunately the Navier-Stokes equations are notoriously difficult to even come up with theoretical estimates. So one of the so-called Clay mathematics $1 million prize problems, which was back in the early 20th century, the famous mathematician Hilbert posed these famous problems that needed solving. Several of them were solved, several weren't, but at the end of the 20th century a similar set was put up. And actually finding out whether Navier-Stokes equations have what are called unique solutions which don't have singularities is still an open issue. So if I'm brutally honest, I can't actually answer your question. Except to say that in numerical weather prediction, where you have lots of verification, the move over the last 3 or 4 decades to higher and higher resolution has had demonstrable impact on skill. There's no question about it. We can now do 10-day forecasts that were only sort of 3-day forecasts a few decades ago, and part of that's due to satellite data, but a lot of it's due to much higher resolution models. But there isn't some uber theory, actually, which will answer your question of exactly how, the solutions converge to truth. And there'll still be the necessity to simulate uncertainty in things like cloud microphysics and some of the aerosol processes. But what you'll be able to get, and there's no doubt about this, is things like these kind of extreme weather events, like the California drought, like the flooding that occurred in the UK a couple of years ago. These are fairly large-scale, persistent weather patterns which require jet streams, where the jet streams are buckled, and I think there's very good evidence that sort of the simulation of those circulation patterns will be much better handled. Just to give you an example, these big anticyclones are fed by weather systems that go around these anticyclones, feed what is called potential vorticity into the anticyclone, which keep them spinning in an anticyclonic sense. It's a bit like the Great Red Spot of Jupiter. That's believed also to have this mechanism of nonlinear eddy transfer, which is feeding energy into the large scale by these very small scale peripheral eddies. And that's something which is currently poorly done at this 100 kilometre scale that will be certainly better done at, say, a 1 kilometre scale. So I'm fairly confident about regional weather patterns, but you know, as I say, I can't appeal to some uber theory of Navier-Stokes to answer that question. I just feel that it's such an important problem, and in a big way, this is not a big amount of money compared to the impacts of climate change, that I think just should be a no-brainer, I hope.
Yes, it's spoken very honestly and modestly about the scientific contribution and the need for additional computational power. But ultimately, when it reaches the political level, all of your work may simply be hammered into a regret analysis. Do you not find that distressing?
Could you be a bit more explicit what you mean by that?
Yes, in a regret analysis, which is the kind of calculation that may be made at the political level, a number of options, quite often a modest number of options, in terms of government spend on remediation, will be compared against a range of possible outcomes of the sort that you described as the outputs from your model. So all of your work would be reduced to actually one page of A4, and that ultimately would be the calculation that would determine the likely political choice in terms of expenditure on the problem.
Well, as I say, I've been, for example, on the flooding committee in government, and you know, I don't think it's reasonable to say it's all been boiled down to one page of A4. I mean, the whole question about how bad, you know, we've had these 2 extreme flooding years. Is this the new norm? Can we expect this to happen? You know, what we're talking about 1 in 200 years, is this now becoming 1 in 10 years? I mean, that is going to determine expenditure on infrastructure. And the UK is one of hundreds of countries. So I hope, and you know, if you have a global model, you have output for every country that needs such information. So I feel intuitively that even if it's 1 page of A4 per country, at least that's 300 pages of A4 or something. How many countries in the world are there?
Thank you.
I'm not as pessimistic as you seem to be there.
Thank you. I was wondering whether we could...